You know that sound, right? That little crackle when you pull off a wool sweater in the dark? Or that tiny, surprising zap you get from a doorknob? Well, that's static electricity. It's this force we run into all the time, but it's got some really cool secrets. So let's dive in and figure out the science behind this everyday mystery.
Okay, let's start with an absolute classic. We've all done this, right? You rub a balloon on your head, and poof, it's like magic. It just hangs there, completely defying gravity. So what is actually going on to make that balloon so clingy?
When you create that friction by rubbing the balloon on your hair, you get this really strange attraction. You can actually see the individual hairs reaching out and sticking to the balloon. This right here, this is our first clue.
So this mysterious ability, this stickiness, it has a name, electric charge. It's a basic property of matter, just like, say, mass is. And here's the important part. It comes in two flavors, positive and negative. These two are the absolute key to understanding everything else. Okay, so if everything has this property, where is it hiding? And did we actually create it just by rubbing a balloon on our hair? Well, to get the answer, we have to zoom in. I mean, way, way in. The real secret isn't on the surface of the balloon or your hair. It's deep inside them, down at the atomic level. Yeah, we're talking about the atom, the basic building block of literally everything. And that's where we're going to find the source of these positive and negative charges.
Think of an atom like a tiny solar system. In the center, you've got your nucleus, which has protons, those are our positive guys, and neutrons, which, you guessed it, are neutral. And then zipping around the outside, you have the tiny little electrons, and they carry the negative charge.
So here's the deal. It's all about balance. In a normal everyday atom, the number of positive protons is perfectly balanced by the number of negative electrons. They just cancel each other out, so there's no overall charge. But if you mess with that balance, if an atom gains or loses an electron, suddenly it's a charged atom.
And that brings us right back to our balloon. See, the friction from rubbing doesn't create charge out of thin air. It just moves it around. It gives those little electrons just enough of a kick to literally jump from your hair over to the balloon. So now your hair has lost electrons, making it positive, and the balloon has gained them, making it negative.
All right, so we've separated the charges. We've got a positively charged object, your hair, and a negatively charged one, the balloon. Now for the really fun part. What happens when these charged things meet other things?
Let's try another experiment. Imagine you take two balloons and you rub both of them with a piece of wool. Now both balloons have grabbed extra electrons, so they're both negatively charged. And when you bring them close to each other, they actively push each other away. They repel.
And that brings us to one of the most fundamental rules in all of physics. Like charges repel. It doesn't matter if it's positive and positive or negative and negative. If they're the same, they will always push away from each other, period.
But what about the balloon and the piece of wool it was rubbed on? Well, the balloon got negative because it stole electrons from the wool. That means the wool is now left with a positive charge. And when you bring them near each other, they pull together, they attract.
And there it is, our second great law, the one that finally explains why the balloon sticks to your hair. Unlike charges or opposite charges, attract. The negatively charged balloon is pulled toward your now positively charged hair. It's simple, it's elegant, and it's incredibly powerful.
But here's a cool little twist. You might think that seeing attraction is proof that something is charged, but it's not the whole story. The real, definitive test for charge is actually repulsion. Why? Because a charged object, like our balloon, can also attract something that's totally neutral, like little bits of paper. But it will only ever push away another object if that object has the exact same charge. So repulsion is the only surefire proof.
So we've totally cracked the case of the clingy balloon. But this whole thing is so much more than just a party trick. This tiny little force, born from electrons jumping around, has some massive implications in our world. Some of them are incredibly helpful, and some are downright dangerous.
Let's go back to that doorknob zap for a second. When you scuff your feet across a carpet, your body is basically collecting all these extra electrons. You're building up a negative charge. Then, when you reach for that metal doorknob, which is a great conductor, all those trillions of electrons see an escape route. They make a huge, sudden jump, and that's the spark you see and the shock you feel.
So this force, it really has two very different sides to it. On one hand, we figured out how to harness its power for amazing things, like inside every photocopier. But on the flip side, on a much, much bigger scale, it's the exact same force that creates the terrifying destructive power of lightning.
A photocopier is basically a masterclass in controlling static electricity.
It starts by creating a positively charged image of your document on a drum. Then, it sprays on this negatively charged ink powder called toner. And since opposites attract, the toner sticks only to the charged parts. Transfer that to paper, and boom, you have a perfect copy. It's genius, really.
Now, let's just scale that idea up, way, way up. Inside a storm cloud, you have ice crystals and water droplets rubbing against each other, separating charges and creating these huge positive and negative zones. When the difference in charge between the cloud and the ground gets big enough, the air just can't handle it anymore. And the result is a massive, giant static shock that we call lightning.
So how do we possibly protect ourselves from something that powerful? Well, the solution is a really simple but brilliant idea called earthing, or grounding. The Earth is just so massive that it can act like a giant bank for electrons. It can either take in a huge surplus of them or give them out to fill a deficit, basically neutralizing any charged object that's connected to it. It's exactly why lightning rods on tall buildings run all the way down into the ground. So, from a balloon that clings to your hair all the way up to a bolt of lightning, static electricity is this incredible reminder that our world is run by these powerful, invisible forces. We've just learned how to see the effects of tiny electrons on the move, which kind of makes you wonder, right? What other unseen forces are shaping our reality right here, right now, just waiting for us to figure them out?